Now I'm recording. Sorry about that. To apply the first derivative test. And so I'm going to write down the example, and as soon as you guys have the example written down, let me know and we will work through it together. So tell me in the chat when you guys are ready to do it. Three people ready, 4. Okay, good. So here we are asked to find the intervals of increase and decrease and the local extrema. So we're going to apply our test for increasing, decreasing, which we know is part of the first derivative test. And the first derivative test, is the thing that allows me to find the local extrema. So like this part right here is the first derivative test. And the first step of our first derivative test is to take the derivative and simplify. So here, I'm going to rewrite f of x. F of x is equal to 3, x squared minus 1. A cubed root is what power? You got it, to the power of 1/3. So now we take the derivative. And here, this is just a simple chain rule. So I bring down the 1/3. So I have 3 times 1/3, which is just 1. Hello. Okay. And then we have, so f prime of x, I bring down that 1/3, so I have just 1. Then x squared minus 1 to the negative 2/3, and then I pull out the derivative. Remember though, for the first derivative test, when we find our derivative, we want to simplify, and simplification involves getting rid of negative exponents. So remember to simplify the derivative. This involves getting rid of negative exponents. Then our second step is to find our critical values. Where do critical values occur? You guys remember? What do I do to find my critical values? 0, so f prime equals 0, and you got it, Gwen. Good job, Yasmina, good job, Gwen. F prime equals 0 and f prime does not exist. So here we're gonna start with f prime equals 0. And we'll remember when we have a fraction, that's like setting the numerator equal to 0. So here I'm setting 2x equals to 0, and I just get x equals 0. So that's one critical value. And then I'm going to do f prime does not exist. F prime does not exist here is x squared minus 1 to the 2/3. But remember, we don't have to take the power with us. Here we're setting the denominator equal to 0. And what values do I get there? You got it. I get plus or minus 1. So this gives me x is equal to plus or minus 1. Now, this brings us to, we were asked to find our local extrema here. So we are going to say, up here with our guidelines for the first derivative test, when finding the critical values from f prime does not exist, I need to determine if they're discontinuities. So here, I'm going to the first derivative test. I need to determine are 1 and -1 discontinuities. And really, I can do that by plugging them into the original function. So here I'm doing f of 1 is equal to 3 times 1 squared minus 1 to the 1/3. And what does that equal? What does that equal here? You got it. That's a 0. And does 0 exist? Yes, 0 exists. So this is not a discontinuity. We didn't get any division by 0. We didn't get a negative under a square root. So when I plug in the -1, I actually get the same value. So here, no division by 0, no negative under a square root, f is continuous. Okay, so this brings us to our third step, and we're really continuing to do the steps for the increasing, decreasing. We just had like a little first derivative test break. We wanted to check those things. And here we're setting up our table of values. So we're going to use the letter I to represent interval. And my first interval, -∞, what's my smallest critical value? You got it, Gwen. It's -1. So I go up to the smallest critical value. Good job, Cyrus. And then I always start where I ended. So -1, where's the next place I'm going to go? Good job, Cyrus. To 0. And then my last critical value is 1. So I go up to 1, and then I finish at infinity. So I'm basically creating an interval from -∞ to infinity, where I'm just taking out those critical values. And then TV is for test value. I pick a value on each of my intervals. What is a good test value between -∞ and -1? -2. And so then I'll just go -1/2, +1/2, and +2. If I wanted to, for example, on that last interval, pick 8,484, could I do that? Yes, because it's between 1 and infinity. Between -1 and 0, if I wanted to pick -7643129, I could pick that. But as Mikael says, why would I want to? I wouldn't. It makes sense to pick values that are easy to plug in. All we're doing is picking some value on the interval. It doesn't matter which one, but it does make sense to pick something that's easy to plug in. I would much rather try to plug in 1/2 than 0.79846, for example. Okay, so then our next line is f prime, where we're looking for the sign of f prime, and our last row here is f. So then I'm plugging those test values in to my original, not to my original, into my derivative. So I'm looking at f prime of -2. So that's like 2 times -2 over 2 squared minus 1 to the 2 over 3. Now all I need here is the sign. So I can look at the top and say that gives me a negative, and on the bottom that gives me a positive, which means the whole thing is negative. Now I just want to point out that that 2 on top means that I'm squaring this thing. If I square something, can it ever be negative? No. So an even number on top means that it will always be positive. And that's really useful if all I'm looking for is a sign, because then I can be like f prime of -1/2. Well, the top is negative, but the bottom is clearly positive because it's always positive. So then we have a negative value there. F prime of +1/2, well, now the top is positive, but the bottom is still positive because it's always positive. And f prime of 2, we have the same thing. I know that the bottom is positive, and now the top is positive too. Did I have any discontinuities that I need to label here? In my step 2, when I checked that prime does not exist, did I find any discontinuities that I'm going to need to label? No. So I don't have like any vertical asymptotes to label. That's important because remember, discontinuities cannot be max or mins. So when it's negative, is f increasing or decreasing? It's decreasing. You got it. So that's going to be decreasing, decreasing, increasing, increasing. And now I know that any of those things, they're not discontinuities, so they can be maxes or min. Are any of them max or min? Are any of my critical values max or min? Good job, Gwen. And what's happening at 0? So something's happening at 0. I've changed from decreasing to increasing, so I have, you got it. So this is a min. And now these right here, that -1 and 1, these are values where it is continuous, but not differentiable. What are things that can occur when it is continuous but not differentiable? Cusps and corners. And vertical tangent lines. Good job, Mikhail. Good job, Gwen. So in other words, I know that those are either cusps or corners or vertical tangent lines. Okay, now we're going to make our conclusions. And our conclusions are that this is decreasing on negative infinity to negative 1, union negative 1 to 0, and it is increasing on 0, 1, union 1, infinity. So that's my answer to the first part of the question. Now for my answer to the second part of the question, I have a local min at x is equal to 0. But remember, when we're stating local max and min, we always also want to state the y value. So I'm looking at f of 0. So this is 3 times the cubed root of 0 squared minus 1. You cannot, Moreno. That's actually a really good question. So can I just say that it's decreasing from negative infinity to 0? And the answer is no, because at negative 1, I have that critical value, which means at negative 1, I've got a cusp or a corner or a vertical tangent line happening, which means that it's actually not increasing or decreasing there. So like if I have this happen, and I'm going to look at a graph at this in just a second. So I could have something like that and then have it keep decreasing. But at this little point right here, we actually can't say that it's decreasing or increasing. It's not doing either. It's changing. And so we actually do have to separate that negative 1 away. Does that make sense, Moreno? Slash everyone else? Good. Okay. So what is the cubed root of negative 1? Anyone? You got it, Dean. It's negative 1. So this is actually negative 3. So my local min is at 0, negative 3. So I can easily know that it's negative 1. Remember, cubed roots are asking me, what do I multiply by itself 3 times to get negative 1? And the answer is negative 1. Does this thing have any local max? No. So we would just say no local max. Okay, are there any questions about this problem? I'm actually going to graph it for you guys in just a second, but so we can see what we just did, but are there any questions as of right now? Okay, so our goal with this stuff is to hopefully by the end of the week have a whole bunch of stuff that we can mix together so that we can eventually graph functions. We don't have enough right now to like easily graph the things, but we do have a start. So I'm going to graph this thing, but I'm going to talk about a couple things that go into that graph because eventually you're going to be the ones graphing. So right now, what I have is 3 points that I know 100% are on this thing. I know, for example, that 0, negative 3 is a min. I also know that negative 1, 0 and 1, 0 are either cusps, corners, or vertical tangent lines. I also know that on the left side it's decreasing forever, and on the right side it's increasing. And so what ends up happening is something that looks a bit like this. And right here, it turns out that these things are vertical tangent lines. Which I'm just not that great at drawing, so I'm going to try that one more time. There we go. Okay, Are there any questions about this? Then we're going to learn a new rule. So what we were just doing here is finding increasing, decreasing, and using that to find local extrema. Well, we have another theorem called the extreme value theorem that gives us more information about how to find global extrema. So that min that I have on that graph up there, that min that I have on my graph up there, that's a local min. Local. Is it also a global min? It's lower, the y value is lower than anywhere else on the whole thing. So it is also a global min. The information that I had in this problem from the graphing was enough to see that it was a global min. So what the extreme value theorem does is it gives us a different way of finding global max and min when we're only looking at small chunks of the graph, so on a closed interval. So here, if you look at this graph that I've drawn, we're just looking at like a chunk of the graph. So the closed interval in question here is from A to B. Does this graph have a global minimum? Yeah, it's right there. It's the place that's lower than everywhere else on the whole graph. What's the derivative at that place where the global minimum occurs? You got it. Here I can say that f prime is equal to 0, and this is a horizontal tangent line. So maybe you're seeing why we focused so much on horizontal tangent lines earlier in the class. Does this graph have a global maximum? Remember how we defined a global max? The y value is higher than anywhere else on the whole thing. Does this have a global max? Where? You got it. This b right here at x equals b is my global max. And it turns out that that global max occurs at an endpoint, at an endpoint of my interval. I could also have something like this happen, where over here, this is my global min, which is occurring at an endpoint. And this is my global max, which is also occurring at an endpoint. Or I could have something like this occur. And I'm going to call this place where we have that corner C. Does this have a global max? Where is the global max at what x value? So global max we're looking at here. Is it going to be C or is it going to be B? It's going to be the C. So that right there is my global max. So it's my global max. What is the derivative at that value? What is the derivative at my global max? A corner thing going on. You got it, it doesn't exist. So here f prime does not exist. Now here, these y values are the same. So here we actually have two global min because the y values are the same for both of them, and those occur at endpoints. Okay, so what the extreme value theorem tells me is that if I only look at a small chunk of the graph and it's continuous on that small chunk, then I'm gonna be able to find global max and min. Hands down, they're just there. So let's actually state this thing. So the extreme value theorem says that if f of x is continuous, and this is important that it's continuous on a closed interval, then there will be a global max or min on that interval. Or rather, global max and min. And remember, we said global is sometimes referred to as absolute. So we'll have global or absolute, max, and min on that interval. And that is the extreme value theorem. But we're going to add a little line to it that says that the global max or min will either occur at endpoints, as we saw in the graphs, or we saw that it could occur when f prime equals 0 or when f prime does not exist. And those are critical values. So or at critical values. And that is my extreme value theorem. Okay, so I know you guys are still writing, but just do you have any questions about what this theorem is saying? Because I'm going to write some guidelines for the theorem, and that way you can get them all down at once, and when you're done, you can let me know. Any questions before I start writing the guidelines? Okay, so I'm going to write some guidelines for how to apply this test so that you can get everything down, and when it's all down, let me know. Guidelines for applying the extreme value theorem, which from now on will be referred to as EVT. So first, we want to let f be continuous on a b. So we're going to have a kind of zeroth step here that tells us to check if it's continuous. Find the domain and see if it's continuous on the interval. Which will bring us into our actual steps. We need to find critical values. So we find the critical values of f of x on the interval. And then our extreme value theorem tells me that those might be global max, but the endpoints might also be global max. Those might be global min, but the endpoints might also be. I know that a global max or min occurs when the y value is higher than everywhere else. So we're just going to check y values. So the next thing that I'm going to do, my step 2 here, is to find the values of f at the critical values. And then our step 3 will be to find the values of f at the endpoints. And then our step 4 will be to conclude. The biggest y value represents the global max, and the smallest the global min. And I just want to point out that steps 2 and 3 are often combined and done at the same time. Okay, I'm going to stop talking for a minute. Let me know when you have these guidelines down, and we will do a practice problem. It's a lot of you, but not quite all of you yet, so I'm going to give you guys a couple of minutes more. Gwen, we're going to do it, and then I think you'll understand. When we actually do an example, I'll go back and like refer to the steps, and I think it'll make sense when we do that. All right, that is most of you. Let's move on to our example then. And so if there are steps that don't make 100% sense, like I said, when we do this example, hopefully that's going to clear everything up. So my example will be find the global extrema of f of x is equal to e to the x squared times x squared minus 5 on the interval -1, 3. And so for our step 0, well, actually before we talk about the steps, the clues in this problem that we should be using the extreme value theorem are the fact that 1, we're asked for global extrema. This could also be absolute extrema. And 2, the fact that we're given a closed interval. These two things right here are big clues that I should be using the extreme value theorem. And you'll notice the extreme value theorem does not involve a table of values. So the difference between the first problem we did today and this is actually quite major. So if you can't look at this and recognize which one you need to do, you might do the wrong thing, and then I can't really even give you part marks. So you really need to be comfortable with recognizing that means to do these steps that we have right here. So we're going to follow our first step, or our 0th step rather. Is there any division by 0 or negatives under a square root? Nope. No division by 0. No negatives under a square root. So this means the domain of this function, we don't have any problems, is just R. The real numbers, which you might also see written as -infinity to infinity. So that brings us to our first step, which is to take the derivative, because I need to find the critical values. So we're taking and simplifying the derivative. What rule do I need to apply to calculate my derivative here? You got it, a product rule. So f of x, f prime of x, is the derivative of the first times the second plus the first times the derivative of the second. So this is e to the x squared. We have a chain rule here, times 2x times x squared minus 5 plus e to the x squared times 2x. And then we want to simplify this thing because we need to find critical values. So we need the greatest common factor. Simplify. So what is our greatest common factor here? Is it just 2x? That's part of it. Is that all of it? We need the e to the x squared as well. So this is 2x e to the x squared. So I'm going to factor out that greatest common factor. So I have 2x e to the x squared. What's left in my first term? X squared minus 5. And here I want you guys to be careful. I'm using the whole thing, which means there is a 1 left there. Good job, Dean. So be careful, it's easy to forget that 1. It's easy to think, oh, I used everything, there's nothing left. In this case, that nothing is a 1. So then this is equal to 2x e to the x squared times x squared minus 4. And this is a great simplified derivative for finding critical values. Is it a great simplified derivative for finding a second derivative? If my goal were to find a second derivative, is this the best form? What would be the best form? Or rather, what would be a better form for finding the second derivative? So what would be a better form for finding the second derivative? Tell me in the chat what you think. This is already the simplified form. So what would the simplified form for a second derivative look like that would be different from this? No, not that, Emil. Because, so I want to point out, I want to remind you, we've said that for finding higher derivatives, less product rule, less quotient rule, good. More power rule, good. So we're looking for less quotient rule, less product rule. Right now, I sort of have a triple product rule happening. With what Emil suggested, I've separated it so that I have 2 product rules. So we still kind of have 2 product rules. Logarithmic, no. So we said that in this case, separating the e part from the polynomial part will easily turn this into just 1 product rule. So I could take that 2x and distribute it so that I just have e to the x squared times 2x cubed minus 8x. And suddenly, I only have 1 product rule, as opposed to a triple product rule or 2 product rules. Do you guys see the difference between that? And do you see how this is better for the second derivative? Are there any questions about what we just, how I made that determination? Good. That said, the form that we have here is better for critical values because it's totally factored. So I'm now going to set f prime equal to 0, which is like saying 2x e to the x squared minus 4 equals to 0. So I'm separating each one of these. 2x equals 0 gives me x equals 0. E to the x squared equals 0. When does that happen? Anyone? Well, what's e to the power of 0? If I replace x with 0, what do I get? 1. E to the 0 is 1. The answer here is never. So if that's not something you're comfortable with, you got it, Mikhail, you got it, Deuce-Main. If that's not something you're comfortable with, it actually is. And it's one of the points of doing this problem right now is make sure that you are comfortable with the fact that e to a function will never equal to 0. So 2, no. E to the g of x equals 0, never. And then last thing we have is x squared minus 4 equals to 0. And when does that happen? x equals to plus or minus 2, you got it. And then I'm going to do f prime does not exist. Is there any division by 0 or negative under a square root here? So this also never happens. So we're just going to write never here. Now step 1 says I only care about the critical values on the interval. My interval is -1, 3. Are all of my critical values between -1 and 3? So here I got x equals -2, 0, 2. Are all of those between -1 and 3? Are we sure? Are any of them, which one might not be? -2. So I don't care about that -2. It's not on the interval. Not on interval. Good. So now we're at steps 2 and 3, which I'm going to do together. So we know that the global max and min occur at the endpoints and the critical values. So I am going to evaluate the original function f of x is equal to e to the x squared times x squared minus 5. I'm going to evaluate the original function at those values. And the reason I'm going to do that is because I know that the one with the highest y value is going to be higher than all the rest of them. So it's going to be the absolute max. So I'm plugging this in, this -1, into my original function. I get e to the -1 squared times -1 squared minus 5. And that gives me -4e. And then I get e to the 0 squared times 0 squared minus 5, which is just -5. Then I get e to the 2 squared times 2 squared minus 5, which is -e to the 4th. And then I get e to the 3 squared times 3 squared minus 5, which is positive 4e to the 9th. So I just plugged these in to the original function. And now my step 4 tells me that I can make a conclusion from this. So I need to compare these values and figure out which one's bigger. That might be challenging in this form though. So I'm going to plug them into my calculator and get that -4e is approximately -10.87. Well, -5 is just -5. E to the 4th is approximately -54.598. And 4, you got it, Mikhail. And 4e to the 9th is 32,412.33. But as Mikhail pointed out, it's also the only positive one. So it's clearly the biggest. Which one's the smallest? F of -1, 0, or 2? You got it, Dean. E to the -4, good job, Mikhail, the third one. This is the smallest. So I'm comparing those values, and I can therefore make my conclusion that my absolute max is at 3. And here I want to include the y value, but I need the exact value, not the decimal, for e to the 9th. So you guys keep losing points for decimals in your group work. Hopefully eventually you will learn that I don't accept them. So I need not a decimal here, but the actual value. So -1 is nothing. -1 is just one of the endpoints. 0, we actually don't know. It could be a local min or it could be a local max. Because I don't know what's happening on either side of it, whether it's increasing or decreasing. It also could end up being neither. I just know it's a horizontal tangent line. So here, hang on, I'll draw a picture, Gwen, in just a second to show you. So here I have my absolute min at 2e to the fourth, to negative e to the fourth. And this is my final answer. Now, Gwen said, does that mean these are mins? And the answer is that this one is, -1 is therefore just an endpoint. It wasn't a critical value. It's not anything important. It's just an endpoint. And as for this -5 right here, the 0, -5, I actually don't know. I could have a min there like this. I could have a 0, -5. I could actually have a max there that looked something like that. Or I could just have a horizontal tangent line there that looked something like that. And I don't have information about that, what that is, because I didn't do a table of values to see if it's increasing or decreasing around it. All I know is it's a horizontal tangent line. Does that make sense? It seems likely that it's actually a max, if I'm not mistaken. If you like kind of look at what's going on with this and the fact that f of 2 is a minimum, it kind of tells you that f of 2 might be doing that, which means at 0, it's going to have to be doing that. So it seems likely it's actually a max, but I'm not going to ask you guys to think about that type of thing for this question. I think it actually has to be a max. I would wager this function looks something like this. Kind of like a W. Okay, are there any other questions about this? And do you understand the steps that we followed? Did that help you to kind of go back and put together what each of these steps means and what their purpose is in the actual process? Okay, let's do another example. So I want to point out the example that I'm doing today, this question, the first question, they're useful in helping us understand how the extreme value theorem works, how the first derivative test works, but also this part, where I simplified the derivative and set it equal to 0. Each of the problems I'm doing today has a very specific simplification process that happens and a very specific type of equation that you need to solve. And you need to be comfortable with all of these. So there were 2 things that you should be getting from these problems today. Like, what is the extreme value theorem, but also what type of equation did I solve there? What type of simplification did we have to do? So this brings us to our next example. Find the absolute extrema of f of x is equal to x squared, the cubed root of x plus 1 on -1, 4. And again, we have that closed interval and we have the absolute word or global here. And these 2 things tell us that we should be using the extreme value theorem. Okay, so step 0. Is there any possible division by 0 or negatives under a square root? No, so there's no division by 0. No division by 0. And also this is a cubed root, not a square root, so no negatives under a square root. So then my domain here is r, or negative infinity to infinity. We don't have any problems. We move on to the first step. And the first step tells me to take the derivative and simplify it and find the critical values. And what rule do I need to take this derivative? The product rule, and inside of the product rule, the chain rule. Good job, guys. So f prime of x is the derivative of the first times the second plus the first times the derivative of the second. And we need to simplify, so we're looking for our greatest common factor. What is our GCF here? So let's start with the 2. There isn't a 2 on both sides. Then we move to the x. Is there an x on both sides? What has the lowest power, the x or the x squared? The x. So we bring the x. Then we move on to the x plus 1. Do I have an x plus 1 on both sides? So which has the lowest power, the 1/3 or the negative 2/3? Negative 2/3, you got it. So that is my greatest common factor. The x plus 1 has a power of negative 2/3 in the greatest common factor. So then I want to factor that thing out. So I'll have x times x plus 1 to the negative 2/3, and then I open my parentheses. I didn't take the 2 with me. I'm going to leave that blank for a second. I'm going to go over to the other side. I only took one x away. I didn't take the 1/3 with me, but I did take all of the x plus 1s. So we've talked about this a lot, largely before the midterm. I had 2 x's. I took one of them away. So how many did I have left? 1, because I started with 2 and I took one of them away. Over here, I started with 1/3 x plus 1s. So I started with 1/3 x plus 1s. How many of them did I take away? I had 2 x's. Look, there's 1 x on the outside. I took 1 away. Now I'm starting with 1/3 x plus 1. So this is where I am here. I have 1/3. How many am I taking away? I'm taking away negative 2/3 x's. You got it. So that means I'm doing 1/3 minus negative 2/3, which equals to 1, which means my new power in both of these cases is 1. And I'm wondering if maybe you guys are feeling quite glad that this did not occur on the midterm. That said, note that we did do this before the midterm and it did not show up on the midterm, which means that there's a high likelihood that it will show up on the final. So you guys need to be comfortable with this, dealing with those exponents and the fractional exponents and the negative exponents. So now I need to combine like terms, expand and combine like terms inside. So I have x times x plus 1 to the negative 2/3, and then I have 2x plus 2 plus 1/3 x, which is x times x plus 1 to the negative 2/3 times 7/3 x plus 2. Is that my most simplified form? Or is there a thing left that we need to do that we, for example, have already talked about today? What do I need to do to finish this thing? I need to deal with it. How can I deal with that negative 2/3? Division, exactly. So remember we've said negative exponents. We don't want negative exponents in our simplified form, so we bring those negative exponents down. So I have 7/3 x plus 2, and then I bring that x plus 1 to the 2/3 to the bottom. And that's important because now that's going to go not for where the derivative equals to 0, but for where it does not exist. So now I'm doing f prime equals 0, and f prime does not exist. So that's my numerator equals 0, and that's my denominator equals to 0. So now I'm setting my numerator equal to 0. We're almost done here, guys. So here I get x equals 0, and here I have 7/3 x plus 2 equals 0. I bring that 2 to the other side, and then I multiply both sides by 3/7 to get x is equal to negative 6/7. And then for the does not exist side, that's when I'm setting the denominator equal to 0 to get negative 1. Are any of those not on my interval? Because I want to move it to the other side. So if I were to multiply by 7/3 here, so if like I do 3/7 times 7/3, what happens is they cancel out and that just equals 1. But if I were to multiply by 7/3 on both sides, then I would get 49 over 9x, and that wouldn't move the thing over to the other side. So like alternatively, you could even think of it as like 7x over 3 is equal to negative 2, and start by saying, okay, so I need to multiply by 3. So that cancels things out, and I get 7x is equal to negative 6, and then I divide by 7. Does that make sense? So we're always, when we have a fraction that we need to move to the other side, we're always just flipping it over. Like the goal is to make it 1 on the left side. And if I multiply by 7/3, that's not doing anything to the left side. I mean, another way to think about it even would be to say, I have 7/3 x is equal to negative 2, and I'm just dividing by 7/3. And division by a fraction is the same thing as multiplication by the reciprocal. Does that make more sense? Okay, are any of these not on my interval? I'm sorry, I don't want to keep you guys too late, so let's try to finish this question. Any of these not on the interval? Zero is between negative 1 and 4. Is negative 6 over 7 between negative 1 and 4? Think about it. Negative 6 over 7, if I have like a number line, there's negative 1. Where's negative 6 over 7? Is it on the left side of negative 1 or the right side? It's on the right. So this one is on the interval. You got it. So this is on the interval. Be careful. And so is the negative 1. That negative 1 is an end point. So we have to think about it no matter what. All right, guys, I'm going to try to do this real quick because the last steps are straightforward. We just plug these into the original function. And our original function was x squared, the cubed root of x plus 1. So I'm doing f of negative 1, f of negative 6 over 7, f of 0, and f of 4. And so I'm going to start with the negative 1, and I get 0, and I'm going to do this, and I get 36 over 49, the cubed root of a 7th. And here I get 0, and here I get 16, the cubed root of 5. I'm sorry, I know I plugged those in fast, but I don't want to keep you too late. Okay, and then We're going to put these in our calculators to get some approximations. 27.36 and 0.384. What's the biggest value? The last one, and what's the smallest? 1 and 3. So this has 2 global min. So then my conclusion, and so this was my step 4 here, and now I can conclude based on that step 4 is that I have a global max at 416 the cubed root of 5, and I have 2 global min at -1, 0, and 0, 0. And that is my final answer. I'm sorry I kept you guys a few minutes over. We are done. That is all. I will see y'all tomorrow.